Dear all, so today what we are going to see is the program corresponding to sum of a series of 8-bit data using 8051 assembly language programming. So whenever you have been given a program, what you should understand is what exactly is required of the program, what are the inputs and what are the outputs. That is what you should first think of. So in this sum of a series of 8-bit data, the inputs are going to be a series of 8-bit data. That is the first thing, right? And the second thing is, whenever the name series comes, you need to remember there is always a count associated with that series. Okay, so that also you have to remember. So in this case, you have a count of the number of numbers associated with the series, and what are the series of 8-bit data. Now let us write the test cases. That is the next step. So for test cases, before saving the inputs actually should come from the keypad and the output should go to the display. So for the time being, what we assume is the inputs are coming from the keypad and that is being saved in the RAM, and the output before being given to the display, that is going to be saved in the RAM. So we should start our work, our program basically from taking the inputs from the RAM and giving the outputs to the RAM from our program. That is what we are focused currently on. For example, the test cases corresponds to for a count of 3 we have 3 numbers, so the value is the total sum is 9C. For a count of 5 numbers, I just gave 5 FFs, the answer is 4FB. Now again for a count of 5, I gave 5 different random numbers, the answer is 343. Then count of 6, we gave from FF to FA, the answer was 5EB. So in order to allocate how many RAM locations are required for the output, we need to see the worst case scenario. So you can actually give any number of numbers starting from 00 to FF, and you can give those many numbers. But in this program, we are assuming like our outputs will remain in between 2 bytes. So it will be within 2 bytes. That's our assumption. If it goes after 2 bytes, then you need to allocate more number of bytes as per your requirement. For the time being, we are assuming like within 2 bytes our output will remain. Now the next thing is, how are we going to write this in our RAM? So we assume like our inputs are present in RAM, which basically came from the keypad through the ports, and now it is being saved in the RAM. So how it is going to be saved in the RAM? So let us write the test cases for the different scenarios. We assume the RAM location starting from 50H corresponds to the count and the series of data. So for count of 3, 12, 34, 56, that was the input. The output was 9C as we have written here. Now for a count of 5 FFs is what we gave, and the answer was 4FB. So 2 bytes, so it will be written as 04FB, and we are following the convention like lower address corresponds to lower byte of the answer. So FB was the lower byte, that is why it came to 56, and higher byte was 4, it came to 57. So we are saving the output directly right after the inputs. And for count of another 6, so count of 6, we gave another set of data as above. Those data like AB plus CD plus etc. So the answer was 343. So you should save it in the next location. So again it should come here. We have count of 5. So AB plus CD plus etc. up to FF. So 1, 2, 3, 4, 5. So it came at 55, this one. So the answer was 343. So we will have 43 here and 3 here. So this was the outputs. Like that you should write the test cases. So here what you have to remember is the output locations are not predefined, because it depends on the output locations are right after the inputs. So based on the number of numbers in the input, your output locations will vary. Now coming back to the logic. So if you see, what are we doing? AB plus CD we will get, so initially it was 0. So 0 plus AB we will get AB. Then we will perform AB plus CD. We will get another value. That result plus 34 we will get another result. That result plus 98 we will get another result. And we will get finally the result plus FF, you will get 343. So this is how it works, the logic. So like we mentioned, initially the result is 2 bytes, which is 0000. Then we added the first number AB to it, so we got 00AB. Then we added CD to it, 00AB plus CD, we got 0178. Then we added 34 to it, we got 01AC. Then we added 98 to it, we got 0244. Then we added 44 to FF, we should get 0343. So here what you have to remember always is our all operations are in 8 bits. Like addition is the main operation we are going to perform. So when we perform add, the operand, if you see, the first operand is A along with the second operand. So it performs only 2 byte addition. Okay, so whenever we are doing an addition, the number whatever we have, the 8-bit number will go to the lower byte. Then we add the lower byte of the result to that number. Then we will get the lower byte of the result. Then we added AB plus CD. Then if you perform it in calculator, you will get the answer as 178. But in our case, this 1 will go to the carry flag. That is what you have to remember. It's a single bit. Now you need to allocate, you need to convert that single bit to this byte. The 00 should become 01. So basically what we will do, if there is a carry, your higher byte will get added by 1. Then we add again 78 plus 34. If you look in calculator, it is AC. So our higher byte remains the same. Our lower byte becomes AC. Then AC plus 98. If you look in calculator, it is 144. That is what you will get when you add AC plus 98. Then that 1 should go to the higher byte. That 1 actually comes in our carry flag. So it should go to the higher byte. So our higher byte should get incremented by 1. So our higher byte should become 2. And the lower byte will be 44. Then we add 44 plus FF. FF is our last number. In calculator, if you see, if it is 143. Again, in our case, when we add this 2 8-bit addition or 1 byte addition, we will get 43 in A and 1 in carry flag. That carry flag, since it is 1, we need to add 1 to the higher byte. That is what the logic is. So the flowchart is, our result we have initialized to 0000. Then we take the next number. In the first case, next number becomes the first number. Then we add that lower byte of result to the next number. That is what we added. So AB is added to 00, lower byte of the result. That becomes the result's lower byte. Then we check, is there a carry from the lower byte addition? If it is yes, the result higher byte will get incremented by 1. Then if it is no need to change the higher byte of the result. The count gets decremented, because always in a series, always when you are performing an operation using a series, your stopping condition will always be the count becoming 0. Now we have added one number AB, so 1 is reduced, 1 is subtracted. Now only 4 numbers we need to add, so count becomes count minus 1. Then we will check, is count equal to 0. If count is not 0, again go back, take the next number, which is CD, add it to the lower byte of the result. If there is a carry, your higher byte will become 1, and again the count becomes count minus 1. Is count equal to 0? No. Take the next number. Again this operation gets performed. And finally, once the count is 0, we save the result. That is what we should do. Now coming back to the program, what we will do in the program is change this flowchart into layman's, the flowchart which we explained in layman terms, we are going to convert that to a program. So the first line was result equals 0000. That is what we need to do. So we need to use registers. So for the result, we are going to use, I am just temporarily using 2 registers. You can use any register, R5 and R4. So initially both of this should be 00. So then we have a count that we need to take, that I didn't write here. So take the count, that is also there. You can do it after the initialization, take count. So that count we are going to get it in R0. Then when this is memory looping, right? We need to take the first number in 51, then the second number in 52. So whenever there is memory looping, you have to go for register indirect addressing mode. For register indirect addressing mode, you need to use either R0 or R1. In our case, R0 we have used for count. So R1 is what we are using. So R1 we assign the value 51, because this value 51 actually to the programmer means it's the address of the memory that we know. that we will be doing at R1. That is what we are going to do. Then we initialize the result like in the flowchart we did. Now our next step in the flowchart is take the next number. So for taking the next number, we are going to take the first number. So move a comma at R1. So R1 is 51. So at R1 means at 51. From 51 you will get the first number. We add that number, first number, with the lower byte of the result. So lower byte of the result is R4. We added. Then again your result lower byte has to be updated. Your result lower byte is in R4. So you update that R4 because your added lower byte result is now in A. Then what we will see, whether there is a carry as per the flowchart. Is there a carry? If there is a carry, you need to increment the higher byte. Otherwise, no need to do anything. So you will write JNC L1. If there is no carry, higher byte remains the same. If there is a carry, then what you should do? If there is a carry, we need to increment the higher byte, right? So the higher byte is increment. Sorry, no need to do anything, right? If there is a carry, it comes. If there is a carry, it comes to here. So your higher byte will be incremented. If there is no carry, the count will be decremented. Even if there is a carry, you need to decrement the count, right? The count has to be decremented, irrespective of whether there is a carry or not. So the count will be decremented. Again, it should go back to L2. But here there is a problem. What is the value of R1? R1 value was 51. Now before the taking the next number, R1 has to become 52. So for that you need to increment R1 as well. So R1 becomes 52. Take the next number, add it to the lower byte, then save the lower byte of the result back. Then check whether there was a carry coming from the lower byte addition. If there is a carry, increment the higher byte. If there is no carry, you need to increment the location. So L1 should come above. You need to increment the location, and this process repeats. Finally, once the count comes out, you need to save the result. So for saving the result, already your R1 is incremented, pointing to the location after the last number, right? Before decrementing the count, you are incrementing R1. So when your last number comes, your pointer R1 is pointing to the location after the last number. Now you need to save to that location your lower byte result, because our what we are following the convention is lower address corresponds to lower byte. So move at R1 comma R4. This is the lower byte of the result. If this is not there, check the instruction set if that is there or not. If that is not there, what we will do is we will move the lower byte value to A. Then after that we will move it through A. Then what we should do? Increment R1 pointing to the next location. Again move A comma R5, higher byte of the result. Then you should do move at R1 comma A. The program ends. This is what we need to do for sum of a series of 8-bit data. Thank you.